talk a little bit about the hyperbola. Here's its word description. Hyperbola is the locus of all points in the plane such that the difference of the distances from two fixed points remains constant. So here I have my D1 and my D2, and now let's just do the right-hand side of this. So I'm taking, in this case, D1 minus D2 is the constant, and the other case is D2 minus D1 is the constant. So if I take the difference between them, so I take D1 minus D2 as a constant. Again, throw on my Cartesian grid on that so I can use my distance formula now. And let's call these points where they cross the x-axis. Again, this is the major, also called the transverse axis over here. So if my hyperbola is kind of like two parabolas, joined together, and they're kind of symmetric about the y-axis over here, then I call these my kind of like the vertices, plus and minus a, and over here my foci are at minus c0 and plus c0. So I pick those values for my c and a values. So again, we're going to choose that distance equal to 2a, and we're going to assume that now a is less than c. See, a is part way down to c. So now we'll do the following. We'll take my D1 and my D2, take D1 minus D2, and go through the same algebra that we did for the ellipse by slowly but surely getting rid of a square root at a time. Get rid of this square root at a time. Cancel things out. Solve for the other square root. Get rid of that square root. When all is said and done, we have the following over here. We have x squared over a squared plus y squared over a squared minus c squared is equal to 1. But remember, c was larger than a. Why is that larger than a? We can see on the picture over here. My foci is further to the right of a than that vertex. So what I'm going to do is I'm just going to factor out a negative from this last thing over here and write that as minus c squared minus a squared. So a squared is positive, and c squared minus a squared is also positive. That's equal to 1. Like I did in the other case for the ellipse, I'm going to let that c squared minus a squared equal b squared. So this is my standard form where the major or transverse axis is along the x-axis. It's x squared over a squared minus y squared over b squared is equal to 1. Where now, this is a little bit different because I have c squared minus a squared is equal to b squared, or c squared, when I add a squared to both sides, become a squared plus b squared. So it's a little bit different than the other one. We get the plus and minuses are switching around over here. Now, if I have my transverse axis along the y-axis, so instead of opening left to right, they were opening upwards and downwards, the two separate parts of the hyperbola, then my standard form would look like this. Y squared over a squared minus x squared over b squared. Now, for this case, I have to have a plus 1. Whatever the negative is in front of, when I have it in this form, that is my, if you will, my minor axis. The transverse axis, or the major axis, is the positive term. Now, if this was a negative 1 on the right-hand side, I'd have to change that to make that a positive 1. I'd be back to what I have above. So we'll go over that a little bit more tomorrow. And then if I wanted to shift this away from the origin, all I do is replace x with x minus h and y with y minus k, and I have it shifted for either types of one, where I have my transverse along the x-axis and my transverse along the y-axis. And then we'll look at how do I do the ABCs of my hyperbola. Okay, so I'm not going to go into a problem. We will start by analyzing everything from these two equations over here, the two simplified standard equations, where my hyperbola, again, just like the ellipse, is centered at the origin. So the origin is the center. So there's a symmetry happening here. Minus a plus a, minus c plus c. So the center is at the origin. So in that case, I don't have any x or y terms in this thing. It's just square terms. And that looks like the hyperbola. But it does give you an illustration of how you go x squared over a squared minus y squared over b squared equal to 1. And that was one of them. Or we had, this is transverse axis along the x, transverse along x-axis, and y squared over b squared minus x squared over a squared is also equal to 1. And here's the transverse along the y. Are the two types of hyperbolas. Now, in addition, if we look at the various types of hyperbolas over here, you can kind of see, and we also have a different relationship between the A, B, and C for these. Now we've established that my C squared is A squared plus B squared. That's why I put it for the other one. So here, in both of these, we get C squared is A squared plus B squared. And then if I go along this one looks something like this. And let's just kind of make it over here. So let's take a look, and we have that's A, so A comma 0, and this is my minus A comma 0. And then we have my C value, which is larger than those, in here. So over here, this is my minus C comma 0. This will be my plus C comma 0. And it's going to look something like this. Well, we'll do it in blue. Let's do it in blue, because I've been consistently doing it in blue. So now the question is, how do I determine my, the shape over here? Well, it turns out that if I draw a little box over here, a little rectangular box, now the blue should always be on the outside of the box, but if I draw that rectangular box over here, this height here turns out to be the B value, 0 comma B. 0 comma negative B. And interestingly enough, very interestingly enough, if I then draw two lines through these corners, I get over here, I get that, and I also get this. It turns out that both of those lines are asymptotes. And for this particular case here, put a little room for the other one over there, but for this particular case here, I end up with y equals a plus or minus BA over x. So these are y is plus or minus B over A x, are what we call asymptotes. They're not, vertical or horizontal, but they are what we call slant asymptotes. Meaning, as x goes to plus or minus infinity, in both cases, my graph gets closer and closer to each of those lines. Now, if I switch my transverse axis along this way, so if I were to switch it, instead of my transverse axis going along the x, and this should be in the center because it's not centered. Everything should go through the center. Don't have it drawn precisely here. I don't have a nice graph paper. But if I switch it this way and plug in similar things over here, I'll get this thing over here and this over here. Now my transverse axis, if you will, is the y-axis over here. And I draw my box over here. So this is my A and my, this is, now if I, depends upon how I want to set this up, this is still going to be A. That's going to be B. So let's put this over here as 0 comma A, 0 comma minus A. And if I put my B values somewhere here. And there's a b, b comma 0, and try and get it as symmetric as I can. Minus b comma 0, and if I draw my little rectangular box again, I get the same sort of thing where I'll try and get it to go through the center this time. It should go through the origin right there. Both of them should go through the origin. If not, then made some sort of mistake. Now my y is equal to plus or minus a over b. This switches. A over b x on my slant asymptotes. And of course, I would also have my, foci over here as well. I have the foci here and here, 0 comma c and 0 comma minus c. So that's everything we need to know about the hyperbolas. The new thing we introduced is this idea of having asymptotes. Okay, so it's an elaborate thing, and if we wanted to, we could then analyze if we were to shift this around, meaning I'd have, if instead of my center being at the origin here, if I shifted it to an h comma k, some point h comma k in the xy plane, well, this would be x minus h quantity squared. That would be y minus k quantity squared. And over here is be y minus k quantity squared and x minus h quantity squared. And that would just shift it. Instead of being centered at the origin, it would just move it around. But it would still be a, if you will, hyperbola. Okay, so those are the geometric and then the algebraic forms of what my hyperbolas look like. Very elaborate things, but now they introduce this idea of having asymptotes. So as that means, as in both cases, as x goes to plus or minus infinity, my y value gets closer and closer to plus or minus b a over x. Just a straight line. Same thing over here, as x goes to plus or minus infinity, my y value goes towards plus or minus a over b times x. Just switches. Because now my transverse axis is here as opposed to there. So the blue line is my graph. The green and the red are just additional features that we're analyzing on our hyperbola. Okay, so now we have that. Let's see if we can look at a problem and see how we might figure something out about that. That kind of covered everything we need to know about an hyperbola. So let's take a look at an example of the type of problem we would consider. Let me grab it right here. So analyze and graph the following. So here's an example of a problem where you analyze and graph this following. So I have x squared over 64 minus y squared over 36 is equal to 1. Okay, since the positive is in front of the x squared, that means my x-axis is the transverse axis. So I know it's going to be kind of going along the x-axis. I'll just start to draw it over here. And this is where it's along. So I determine here that a squared is 64, b squared is 36. So that tells me then that a is equal to 8 and b is equal to 6. My c squared is equal to a squared plus b squared. So that's equal to 64 plus 36, or 100. And that tells me then that c is equal to 10. Okay, so I can start to kind of fill in everything. I found my ABCs and everything is good to go. So let's come over here and let's start with my A values over here. Those are my vertices. So let's go over here to 8. Okay, so let's start putting this. We go 1, 2, 3, 4, 5, 6, 7, 8. That's one of my vertices. So 8, comma 0. And then 1, 2, 3, 4, 5, 6, 7, 8. So minus 8, comma 0. Let's put it in while I have it. My foci over here. I go 2 more out over here. That is equal to 10, comma 0, and 2 more out over here. That is 10, comma 0. Now let's put in my B value over here. B is 6. So 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, negative 6. Now if I take my point over here, let me draw it in over here a little more specifically. And let's draw my box, my rectangular box now. And it's not going to be perfect, but I'll try and draw it as best we can. Now, once I have this box, I can then draw my 2 vertical lines. Now, it's not perfect by any stretch, but if you have some graph paper, it'll look a lot nicer. I'm going to try and get it to pass through the origin as best as I can. And there's one. And this is y is equal to the negative of, in this case, we see this is b, which is 6 over 8, which is negative 3/4. The other one goes in the opposite direction. And that's another asymptote. And this is y is equal to positive 6 over 8, or positive 3/4 x. Keep me awake, the x. Why do I use those? Well, those will help me sketch the graph of my hyperbola. So it's going to come over here, and it's going to then come here, and then just get closer to that. Here, and get closer to that. Same thing over here. It's going to start here, and get closer, and get closer. So there's a qualitative sketch of what my hyperbola looks like. And that's this is my B value, which happens to be, in this case, 6, comma 0 and minus 6, comma 0. That's how I've analyzed my hyperbola. Oh, not too bad, hopefully. Let's take a look at another one. For now, we're going to switch my transverse axis. So same sort of thing, but let's take a look at a different hyperbola. You see, it's not too hard to do. It's you find your ABCs, but now with the hyperbolas, we have that extra feature of its slant asymptotes there. Yes, Ashley.
When we look at this and we notice that the foci is on the outside, is that what's telling us that it's a hyperbola and not an ellipse?
Right.
Is that how we would know?
Yeah, well, it's definitely, well, you can see what would happen. I mean, let's just look at the right side of that. So here is my, put the vertex in blue. And we're looking at the distance from, this point to that on a line. So the foci, one of the foci has to be out here. So as this goes around, this distance has to be, the difference has to be constant, D1 minus D2. So it has to it goes around the foci. So it's kind of going around that foci. Whereas an ellipse, when you look at an ellipse, foci is in here, and the vertex is out here, that too has to go around the foci. Can't go outside. it has to contain, the graph of it has to contain the foci, because the foci is one of those points that the kind of the nail is fixed to when you're taking the distance and moving around. And the same thing on the opposite side. And the same thing for the parabola. Instead of at the focal point of a parabola, it's the same thing. Remember the parabola. Is a parabola opening upward. Well, that p-value is here, and that's a focus point, and the graph goes around that foci. Now, the way to notice it from the equation is as a negative. With an ellipse, it's, x squared over a squared plus y squared over b squared. For an hyperbola, it's, x squared over a squared minus y squared over b squared. Or you can flip the roles of x and y. Put the negative in front of the other. So let's take a look at another one that looks like y squared over 25 minus x squared over 16 is equal to 1. That negative sign here, of course with that being positive, tells me it's a hyperbola. And since the y squared portion is positive, this tells me that's the transverse axis. So in this case, I know it's a hyperbola with the transverse axis along the y. That means it's going to open up here and open down over there. So what I want you to do is to try it. Take it from there. Again, we know what's going to happen now. I'll start to sketch it over here. And I'll do all the details as well. But it's going to be opening this way. So you're going to plot your A and your C and your minus A and your minus C here, and it's going to go this way. So see if you can figure out what A, B, and C are, and start to graph that on your own. I know I can do it. I showed you the other one. You should be able to do this relatively easy. To A. So the blue is my actual graph. But now the transverse axis goes along here. And we could also take a quick look at Desmos here, and you'll see the same sort of thing for both of those. I have a Desmos. I gotta get another Desmos graph up here. There we go. Okay, so let me find it. Yes, Colin, you have a question?
I was just wondering where you got 0, 6 and 0, -6 for the
Oh, it should be 5. Excuse me. Yes, yes, yes.
Okay, so should the
5.
the
5.
slope of the asymptotes then be
It
5
would be
over
5.
4x or
Yeah,
-5
then it would be, in that case, it would be 5 quarters. Yep, keep me awake. I was looking at something else over there on the side. Yep, keep me awake there. Going to change a little bit because this is not exactly the right thing, because this would have to shift down. So these are going to go down. Instead of 1.5, they're going to be 1.25. So it's going to come down just slightly, but that's just the idea. We'll just call this -5, and we'll get rid of one of those. And that sort of thing. Yeah, okay, keep me awake there. And let's take a look at that, and then it will come up on our, if you will, over here, you can take your y squared and divide it by 25 minus x squared divided by 16 is equal to 1. Whoop. Okay. Minus x squared divided by 16 is equal to 1. And you can see what the vertices there are. Let's draw 2 lines. Y equal to 5 quarters times x, and y equal to -5 quarters times x. And if I zoom out here, you can see what I'm talking about, them being asymptotes. And you could also plug in the lines over here. Y equal to, what do we have, 5. So y equal to -5. X equal to 4, and x equal to -4. And then if we zoom in, you can see that just as I drew on here, those asymptotes go right through the corners of that little box that we drew there. So it kind of matches everything we did here. This is more precise because it's a nice perfect graph as opposed to what we have otherwise. Okay, this is a great tool for actually understanding what you're seeing and validating it and kind of making it more tangible to you. Okay, that's all we want to do for hyperbolas. We're not going to shift it off the origin. We're just going to keep it that way. But now we've fully analyzed an hyperbola. Now, before the days of calculators, obviously you needed this. And you could then get a reasonable graph of something to understand what's happening. Today, we can go right into our calculators or our web apps, and as you see, in a matter of seconds, analyze everything right there. Okay, we have one last topic to consider, and this is not a hard topic. And what we've been looking at is conic sections, such as my circle, my parabolas, my ellipses, and my hyperbolas. And we've always oriented them relative to the x and y axes. Well, it turns out that, you can intersect those cones at any orientation. So you might get parabolas that look something like this. It's not up or down or right or left, it's at some angle. In the same sense, you could get a hyperbola that does the same thing at an angle. So in general, you might be given a equation or relation that has x squares and y squares and x's and y's and all these other things in it, and you might be asked to, okay, can I in some way understand what type of conic section am I dealing with? So for this, let's go to the textbook again. So here we are, let's move forward with some problems I'll give you. There's just a few things on these, but this is what we call the next section, classifying conic sections from their equations. You could have an ellipse on its side, hyperbolas, parabolas. They could be at a different orientation and moved anywhere in the plane. And they're of equations of this form. A constant a times x squared, a constant b times the cross product of x and y, constant c times y squared plus d, e, and f. Now it turns out that the coefficients a, b, c, d, and f together will determine the type of conic section we have. And in fact, it's going to be a little bit simpler than that. A, b, and c will be actually determining. We're going to find that the d, e, and f, the only thing those will do is, well, the D and E will just shift it away from the origin, its center point, or vertex if you're dealing with a parabola. And the F might kind of change the shape of it a little bit. Now, there's a theorem that says how everything is related. Now, I'm not going to prove this theorem, but we're going to use this theorem. So if we're given this general equation, ax squared plus bxy plus cx plus d x plus ey plus f equals 0, this will give us a parabola if b squared minus 4ac equals 0, taking just the coefficients. It will give us an ellipse if b squared minus 4ac is negative. It'll give us a hyperbola if b squared minus 4ac is greater than 0. Or in some cases, you might get a degenerate case, and that depends upon the f here, that is not a conic section. Now, we will not prove this theorem. There's a lot to it. But you might recognize this b squared minus 4ac from the quadratic formula. There is a relationship. It turns out that the coefficient here that causes our conic sections to be rotated is b. The value of b rotates the conic sections. And the signs of these things have all sorts of meaning as well, too, when you plug everything in. The sign of b doesn't matter because it's squared, but the sign of a and c do matter to see what's happening. So it turns out that if I only consider the a, b, c, and notice that, e, d, and e, and f just kind of change the shape and move it away from the origin a little bit, my real focus is on these three coefficients. Now, if I divide everything by y squared and rewrite it like this, okay, I get this quadratic equation. And that's where these coefficients and their meaning come from. So it is related to the quadratic equation, which is kind of an amazing thing. We're not going to go into that. It's a hard theorem to prove. But you can kind of see where it is related to a quadratic, I get 0 on the right-hand side, equation. So, and then you have real solutions if that's positive. You have, only a single solution if it's equal to 0. You got a repeated solution. And then you have if it's greater than 0, you end up getting hyperbolas. Okay, so only thing we want to do is the following. Let me take us back to that. This is a really short section. So we're given, this is 12.5, classifying conic section from their equation. How do we classify conic sections? So we're given ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. And we can classify them based upon the A, B, C's. D, E, and F, we don't even need to be concerned with it. We just want to classify them. They will do other things. They'll shift it, and they might shift the shape of it a little bit. The F will. We have a theorem that says if B squared minus 4AC is equal to 0, it is a parabola. We know that, no matter what it is, no matter what the signs are and everything else. So the y you could have an x squared and a y squared, and it could both be a parabola. Interesting. So b squared minus 4ac is negative, it's an ellipse. And b squared minus 4ac is positive, it's a hyperbola. So, for example, if you're given a problem over here, such as, I'm given 2x squared plus 3y squared minus 2x plus 4y minus 7 equal to 0. And I want to classify that. What do I do? All I do is I find my A, my B, and then I find my C. And I plug them in over here. So I end up with, B squared, so I get 0 squared minus 4 times 2 times A. So I end up with a negative 24. It's less than 0, so this would yield an ellipse if I was to sketch that and work that out. That would give me an ellipse. That's all it means. Let's take a look at another one over here. Just a couple examples, 2 examples. So now notice this, that one didn't have a b term. This one does. So now if I have x squared plus 6xy plus 9y squared minus 8x minus 6y minus 10 equal to 0. Come over here, I get A is 1, B is 6, and C is 9. I don't care about the other ones. I'm only caring about the first 3. So now if I plug it into my relationship over here, 36 minus, and I get 4 times, 1 times 9, 36 minus 36 gives me 0. This is an equation of a parabola. Even though it doesn't look like it because I got x squares and y squares, well, I can't have both x squares and y squares going on. But the parabola here is no longer, up or down. It's at some angle. I don't know what it is. I don't know if it even goes in that orientation. But the parabola has a different angle for the axis of symmetry rather than just the y-axis or just the x-axis. Now, the reason I mention this, you will see this again in a higher level math course when they start classifying what they call differential equations, partial differential equations. They're going to talk about these parabolic differential equations, and they're going to talk about elliptic differential equations. So this will come back. That's the only reason I do it, is because it is an interesting feature in mathematics that you will revisit. But it's very simple. Just compute this. If it's 0, parabola, negative ellipse, positive hyperbola. That's all it is. And I'm not even going to ask you to graph it or anything like that. Okay, so we are out of time, so let me give you the homework here. And tomorrow we will review for the test that we will take on on Thursday. We're probably going to have some